If you go on Canvas, you get a link to our webpage, and you can find pretty much all the information on the webpage that you need. I just wanted to highlight that in this semester we have a number of projects, and so please sign up for a lab session. There's on Canvas you can fill out this poll assignment thing to basically sign up for one of the lab sessions. It's either Monday, Tuesday, or Wednesday, 7 to 9 p.m. So if you, so please sign up for one of those lab sessions. If you can't absolutely make it, let us know, and we'll try to find some other arrangement. So the idea is for all of the projects, I'll give a presentation like today in lecture about the project, and you'll be given a project handout. So technically and hopefully all you need to know about the project is in the handout and in the presentation, so you can work on your own time. There are open lab hours where you can come in as you wish to work on the project in the lab. But besides that, there's explicitly hours reserved for each set of students. So you have at least 2 hours a week to be in lab, and nobody else will be there, and you can have all the equipment to yourself. So please sign up for the lab session, and please come to your assigned lab session, and each of us will assist with one of the lab sessions. So I think who's our TF? I think she'll do Monday. I'll do Tuesday, and Wenjie will do Wednesday. So anyway, so one of us will be there to help you. And overall, I also wanted to introduce Kevin, who's in the back, who's in charge of all the teaching labs and all around great guy. So please respect all the equipment, all the stuff in labs, because Kevin has to take care of it. So do you guys have any questions about the lab? I mean, the labs or the class? No. Okay. All right. So today we'll do something. We'll do something different. So basically, I'll give a presentation introducing the first project, which is the credit card reader. And one thing to note, we'll record this. Presentation and the lecture, so you're free to ask questions. It just might be cut on the audio, but hopefully we'll post the video as well online, so you can, if somebody wasn't here, you can review it. So, but when is it? Okay. All right. So, well, welcome. Thanks for coming. And the first project for our class will be the credit card reader project that we started last year. And basically, with this project, the idea is that we have all collected all these old credit cards, all the stuff, and then the idea is you can try to find out how the information is actually stored on the magnetic stripe on the credit card. And if you're interested, there's some of my own old credit cards, so you can play around. I hope they're disabled, but anyway. So in this, I guess the project has kind of two goals. One is to just give you introduction to how the magnetic stripe works on credit cards, and just to kind of understand some things. For example, we'll talk about active high and active low logic or signals that are used on the credit cards, but also it's meant as an introduction to this piece of equipment, which is the digital or mixed signal oscilloscope, which you'll be using in lab and in this class, and actually I believe 200 and other classes use the same piece of equipment. So something you get to know, and it's very, very useful. And then in the last part of the presentation, I will talk about how to actually connect the credit card reader, which is this little PCB board, to the scope, and to actually get some things out of the credit card. But before we start, just a few notes about our lab. So this is Hill House 17229. That's our lab space. And please try to respect it and make sure it's clean. You can see everything is nicely organized and chairs are pushed in. So just try not to, try to keep it the way you arrived there. I believe there will be at least 1 or 2 other classes besides us using this lab and the EE senior project. So it kind of helps everybody if you're just kind of keep it nice and clean. And some lab safety rules will have more details, but in general, basically try not to work alone, especially if there's an accident or something. It's good to have another person to be there, so that's good. And try not to bring any food or beverage into the lab. If something gets spilled on the equipment, not so much the equipment, but also you might get shocked. So best, if you have something, just keep it in your backpack and and just drink or eat. You can always go outside of the lab to drink or eat. And please respect the equipment and clean up and put everything away when you're done, so the next group or the next set of people can use it. One thing, now it's not an issue, but in the summer, try to wear long pants and like closed-toed shoes in case something falls, something spills. You never know what happens, so it's good to have some layer of protection. And again, if something does happen or you think something happened, please let one of us know, or there's always 911 or the campus safety you can call. Especially sometimes, if you think you got electric shock, you don't know, just let us know. And like in the movie theaters, know where the exits are in case something happens. And if there's fire, try to get out, but use your common sense. So. Yeah, and then and then last part, basically, again, each of you should sign up for a lab session. So try to go to the session you're assigned to, because we have a limited number of pieces of equipment. So we have only so many of the credit card readers, and we want to make sure that everybody gets their own to use. So go to your own lab session that you're assigned to, and if you don't finish in your own lab session, there'll be kind of open lab hours there where anybody can randomly come in. That will be posted pretty shortly. So okay, so I don't. Do you guys have any questions about lab safety or yeah?
When is the first lab?
Very good. Yes, very good. So the first lab will be starting on Monday or next week, and at the end of the presentation, I'll give you some schedule of the projects. But yeah, so next week, all the excitement starts, and the first exciting thing is the credit card reader. So last year, Kevin actually helped put together this nice printed circuit board, and we have a credit card reader and some digital outputs that you can use to analyze to see what's actually on the credit card. And so the goals for this project again is to basically learn how the data is stored on these on the magnetic stripes on the credit cards, and and not just the credit cards, but there's some random hotel key cards. All of them use pretty much the same standards. So you're welcome to bring your own stuff and try it out. It's that'll be even fun. So hopefully you learn about these magnetic stripes and how the computers or how digital logic can be used to store data, and then also to introduce the scope. All right. So hopefully all of you have seen a back of a credit card. So this is I guess a standard card with standard dimensions. So all the credit cards magically have standardized dimensions that they all follow. Sometimes you may see some cards that are thinner or thicker, but for example, the standards specify how far the edge of the magnetic strip is from the edge of the card. So for example, if you might find somewhere in the pile is a hotel card that it's the dimensions are different, but lo and behold, the magnetic stripes actually line up on the back. So all the card readers and all the cards are in some sense standardized. And so how is the data stored on the magnetic stripe? So each stripe stores up to 3 tracks of data. So you have 3. So you can think of that the material, the magnetic material, is divided into 3 stripes, and different cards may use different ways of encoding the data that's stored there, but basically you can have up to 1, 2, or 3 tracks of data. So for example, on your Yale ID card, I believe they only use two of the tracks, so you don't have to use all 3. And as I'll show shortly, each track is kind of independent, so you can store different data on each of the tracks independently. And all right, so if you dive into what's on the track, so you have the credit card or whatever magnetic stripe card, and then it has 3 tracks, and then each track is actually made of 3 separate signals. So in total, you have 3 times 3, you have 9 signals that are stored on the back of the credit card if it's using 3 tracks. And so what are these signals? So each track has 3 signals that are required to be able to store and read back the data that's stored on the credit card. So the 3 signals are, one is the card present signal. So it basically is used to indicate that the card there's something on the card, and you'll see it see it on the picture better. There's the clock signal. So later in the course, we'll learn about clocking and sequential circuits, but for now it's important to know that basically there's a periodic signal, the clock, that basically is used to tell when to sample the data. And so why is the clock signal on the credit card or on the magnetic stripe card? So basically each of us swipes the card at different speed. So it's basically kind of like a self-reference. So regardless of how fast or slow you swipe the card, basically the clock and then the data signals are aligned, and then whether you swipe it faster or slower, that just changes the kind of the spacing in time. But so that's kind of interesting that within certain limits you can swipe the card very slow or very fast, and it still works. So that's kind of nifty. And the last signal is the actual data signal. So that stores the actual data that's on the card. So you have these three signals that are together used to tell you what's on one track, and then they're replicated 3 times for the different tracks. And I'll keep mentioning it this few times. You can see that there's a little bar over the signal name, and that basically means it's an active low signal. So we already mentioned in class that the active low means that the high voltage or the high value actually means logical 0, and the low voltage or the low value of the signal actually means logical 1. So that's something to pay attention to. All right, and to dive a little bit deeper of how actually the data is stored on the magnetic strip. So basically, the magnetic strip is some sort of iron or some other base material that you can magnetize. So when you write onto a credit card or onto like on the hotel card, when they put it in the machine to encode some information, basically they're writing some data. And the way it's done is basically you create these little magnetizations, or you can think of it just little magnets that are basically the magnetic field is going one way, and then it switches, and then it switches again. So it's basically a bunch of regions that are polarized in different directions. And basically, as you swipe your card, the sensor on the card reader will pick up the direction of the magnetic field. So this is kind of the let's say an analog readout of what the sensor might be seeing from that track. And okay, so you have these regions that are magnetized in different directions, but how do you actually store ones and zeros? So we talked in class that we want to basically store 1 and 0 for the binary data. So what happens is that the density or the spacing of these regions determines basically whether it's a 1 or a 0. So here in this case, you can see that if there's within some region, if there's only one kind of change of the magnetic field, that's going to be a 0. So this is one change, that's a 0. One change again, that's a 0. But in this region, you have two quick consecutive changes, and that's basically encoded. That encodes a 1. So depending on how quickly the changes happens, it's either a 1 or a 0. And again, because you don't know how quickly the card is swiped, there's the clock track. So on the clock track, all these regions are always the same because it always oscillates between 1s and 0, and then all the logic on the credit card reader can basically determine whether the data should be a 0 or a 1. Does that make sense? Any questions? So far so good. Okay, all right. And then so here we get to the active low and active high part. So you can see that when the credit card reader outputs a high signal. So in this case, I should mention we're using a 5-volt logic. So the credit card reader would either output 5 volts or close to 5 volts to represent a high signal, and close to ground or 0 volts to represent the low signal. So when it outputs a high signal, it's actually a 0, and then when it outputs a low signal, it's a 1. So again, kind of when we draw these digital signals, there's always a high and there's always a low. So that's useful to keep track of. And then this is kind of a schematic of what happens when you read the credit card or when you swipe the credit card. So basically, you have your card again, and then this has 3 signals for each of the 3 tracks. And as you swipe it, this is a picture from the spec sheet for the credit card reader head itself. Basically, there's magnetic reader heads that sense the changes in the magnetic field. There's some decoding circuitry that we'll just leave as a black box for now, but you can try to talk about it later if you wish. And then eventually the credit card reader outputs you multiple signals corresponding to what it read. And the magic of animation on PowerPoint, you can see that the specification or the signals that are from listed in the manual are the actual signals that you get on the PCB. So when you go to lab, you'll basically, I don't know if you can see it, but it's the cable's long enough. Basically, all the signals are labeled on the side of the credit card reader. And one thing to note, we omitted to put the dashes on top of the signals to indicate that it's active low, but otherwise you can see that there is 3 signals for track 1, 3 signals for track 2, 3 signals for track 3. There's an input supply voltage, 5 volts, that we're actually not going to use because we're using a separate power supply. And then there's a ground. There are 2 ground signals. So basically all your equipment should always share the same ground. So the scope has I'll show you, there's a probe that you connect the ground to, so everything has the same reference. So yeah, so that's basically you swipe the card, and the reader decodes the signals, and it gives you digital outputs via these pins that you can observe. And so this is if you can't really see it, this is the picture of the credit card reader setup. We have a 5 volt power supply, so unless you plug it in, it's not going to do anything useful. There's the digital output pins that you connect to the scope. There's a 40 pin header in the back. You can actually interface it to the FPGA we'll use later in the semester. So we're not going to use it this time around, but if you're curious, you can output the signals, and then the FPGA could process something. So you could write some logic that does something more interesting with the inputs from the card. And then this is the actual credit card reader head. And then so what happens, basically, you take your card, and if the card stripe faces, so the credit card reader has a read on one head. So sometimes if you go places, you can only swipe it one way. That's because there's only one read head that faces the stripe. Like if you can swipe your card either way, that means they have read heads on both sides. But this one has only read head on one side. So if your card faces the read head, you can think of it that the data kind of is, the start of the data is on the left side, and then it's on the right side. So basically, some more animation magic. You basically, as you swipe it, the credit card reader outputs the signals that it sees on the card. All right, so this is the kind of the image of what you would get from reading a credit card. I'll get into details of how to capture this image using our scope in a bit, but first, again, just wanted to highlight the what's on the card. So again, so there are these 3 tracks. There's the card present, the clock signal, and then there's the actual data signal. And when you swipe your card, you can see that so the top signal is the card present, then you have the clock, and then you have the data signal. So you can see that the card present basically is high. It's so it's high, but it's active low. So it actually means logical 0. So there's nothing interesting happening. And then at some point, the signal goes low, meaning that now there's some interesting things happening. So you should be capturing the data. And then as soon as it goes low, there's a clock signal encoded on the second track that you can see it's very periodically going up and down, up and down, up and down. That's the clock signal. And then you have the actual data as the third signal. And again, since it's active low signals, this actually means logic low, and then this means this means logic 0, and then this means logic 1 because it's low. So for example, somewhere here, what's the data value somewhere here? 0. Perfect. Yeah. So here the signal is high, so the data would be 0, and then here when it's low, it would be actually logic 1. So you can, so this is like 0, 0, 0, 0, 0, 1, 1, 0, 1, da 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 da, and you can decode this this data. And in a second, I'll tell you actually when exactly to decode the data. But as a kind of a note, sometimes instead of having this dash above the signal, later when we write some system Verilog code, you can, by convention, you can say some signal name underscore little n for a negative to indicate that's a logic active low signal. So just some convention. So you might see either way. Okay, so the last bit about decoding the information. So when do you actually read the data? So you have this clock, and then you have the data, but then you have to decide when to actually read the data. So in the credit card, basically you read the data on the falling, what's called the falling edge of the clock. So you have this periodic clock signal that goes high, low, just keeps going high and low all the time. And then the falling edge, as the name implies, is basically when a signal goes from high to low. So you have a falling edge here. What's the opposite of a falling edge?
Rising edge.
Yeah, rising edge. Yeah, we're not very clever. So yeah, so some stuff works on rising edge, but in this case, it's a falling edge. And so what happens is you basically look at the clock signal, and at the time when when the edge is falling, that's the time where you look at the data signal, and that's your data bit. So here we have 1, 2, 3, 4, 5 falling edges. So we should have five bits of data, and then the 5 bits of data would be 0, 1, 0, 0, 1. So that's pretty much it. So if you see the signal on the scope, basically again this is the same image as before. You have the clock signal, and if you squint quite a lot, basically you can line up the falling edge of the clock with the data signal, and you can decode. So this data basically means it's a bunch of zeros, and then here is the falling edge, and you go and look. Okay, this is 1. This is 1, this is 0, this is 1, and it's up to basically it's up to the whoever writes the card, or the mechanism that writes the card, to align the signal such that the change in the data signal basically happens on either side of the falling edge of the clock. So there's some margin of error if there is some jitter. But a couple of questions, yeah.
So on that top track, it has 2 1s, but between those 2 1s, there's a small point which changes into 0, but the clock doesn't change.
Which one here?
Yeah.
Oh, no. So the clock always shows the. I see. So okay, maybe it's not very clear. So there's a high, and then there's a low. So there's a falling edge. There's a high and a low. There's a falling edge, and there's another high and a low and a falling edge. So there's
right. But between those two ones, there's a point that it changes to 0.
Oh.
There's no clock there. So is that just like a mistake?
No. Oh, perfect. Very good question. Yeah. So we're only interested. This is a good question. So we're only interested what happens when it's the falling edge. So basically, you can ignore what happens at all the other times. So that's the way they encode it. And this is probably done because you have to, on the magnetic stripe, you have to basically alternate the little magnets. So I guess the reason for this thing is that there's some short thing that goes up and then goes down again. But yeah, whether this is like this, or if it was just a straight line, you'd get the same data, because all you care about is the falling edge. Yeah.
So the clock track, is it just equal magnetic fields like next to each other?
Yes.
Like, I don't know. So does that mean that you can like swipe the credit card slowly first, and then like halfway like go really fast, and it'll still work?
Okay. Yeah. Technically, it should still work, because so the read mechanism basically it looks at the changes in the magnetic field, and then it decodes the 2 1s and 0s. So technically, yeah, you could swipe it at different speeds, and it should work.
Okay.
and in practice also it's not going to be very precise. The clock itself, I mean, it looks very even, but like I don't like here. Okay, here it's like this low is kind of different size than this low. So maybe it's my hand, or maybe it's the encoding that's different. Yeah.
Is there a standardized number of bits that the magnetic strip outputs, or is that just completely dependent on?
Yes, there's standards. Actually, the first slide, or one of the first slides, mentioned some of the standards. Yes, so there are different standards that basically say how densely you can pack the bits, and it's mostly related to the fact that basically everybody has to, the more density it is, the more expensive the reader is. So there's kind of some trade-off. But yeah, there are different standards, and okay. I mean, we can go back. I'm actually kind of curious now. What's the oh, here? Yeah. So for example, so I don't know if you can see it, but so I guess it's about 200 bits per inch. That's the rough. It looks like the different standards all agree on about 200 bits per inch. And but if you have a better read mechanism, then you could probably do more. And do you guys have any other questions? Okay, let me get past all these amazing animations. Okay. Okay. All right. So. We're almost done. So the one last step is, once you get all the data, you get a bunch of zeros and ones, and then what do they actually mean? So depending on different encodings, and there are basically two main standards, ABA, and there's IATA. So basically people agree on that. It's how to interpret the bits. So for example, in the ABA encoding, there's a bunch of zeros initially that you ignore, and then each group of 5, 1, 2, 3, each group of 5 bits is used to represent one hexadecimal digit. So you have what's wrong with this picture? So we're having 5 bits, but we're using it to represent a hexadecimal digit. So do we have too many, too few?
So you have one extra bit?
Yeah, exactly. So there's one extra bit, and then what the bit is used to is actually to use parity bit. So it's used to detect if there is some sort of, so if you, I don't know, maybe if you're reading very fast, the reader doesn't decode things, and you can capture it by checking the parity bit. So yeah, so they use 4 bits for the actual data, and then 1 bit for the parity, which is basically either even and odd parity. So the idea is that with odd parity, you should have an odd. So within the 5 bits, you should have an odd number of ones. So if there's an error, so if you see like 1 1 0 1 1, then you know there's an error because you're seeing 4 ones, and either it should be 3 or 5 or 1. So I guess in 202 maybe. You learn about some encoding things, so we're not going to dive into it, but basically you just look at the 5 bits, and then according to the standard you decode them into some data, and what does the data actually mean? So final bit of information is that, again, you go from the magnetic stripe to 3 tracks of data, and then within each track there's some useful things stored. So for example, if you look at the credit card, basically you can decode these either the hexadecimal digits, or some of them use a little bit more bits, but you can decode them into, let's say a name. So I guess there's a credit card number and a name, and then some additional data. So for example, for the credit card, basically when you swipe it, in the least you'll find out the same information as written on the front. So the card number is stored on the magnetic stripe. There's the expiration date is stored on the magnetic stripe, and then they might store some other information. So I guess now a lot of the cards, in addition to the magnetic stripe, they come with an electronic chip. So for example, the magnetic stripe might have a bit that says this card has an electronic chip. So when you swipe the card, the terminal tells you, oh, please put it in, and it knows it because on the magnetic stripe it told it like, hey, I have this chip, and I guess use the chip instead of the magnetic stripe. So, so in a few years we'll update this lab to work with the chips, but for now we still have the magnetic stripes, and so it could be fun. Yeah, so let's see. So we have, okay, perfect. So we're on time. So the lab manual has basically all the information that I talked to you about, plus the information about the different encodings and how to actually decode the information. Some useful things. Not all cards follow the standards exactly. So on the initial slides, I listed that each track has a standard associated with it. They might switch it around. They might use the same standard for all the tracks. So to just be careful, sometimes you might do some educated guessing that to figure out what's going on. Yeah, be careful about the active low and active high I already mentioned, and also about the bit order. So at the end of the class, I told you that the most significant bit can come at either end of a set of bits. So that's kind of the way the information is stored on the card. The bit order is flipped from what you would expect. So be careful about that. And then another thing is to watch out whether it's even or odd parity. So whether you use XOR or XNOR to compute the parity bits. So anyway, something useful. And in the end, I guess I hope you have some fun. Basically, we have a bag full of old gift cards, credit cards, metro tickets. I don't know. If you have old stuff, you can bring it in. We'll appreciate it as well. So you can try to see what's on these. And at the end, I'll mention exactly what's the required part and what's the optional part. But there's this pile of cards that, yeah, hopefully doesn't have useful information about me on it. But anyway, you can. So the second part, which actually might be even more exciting, is this mixed domain oscilloscope that we got two years ago or last year, I think. 2 years ago. 2 years ago. So still rather new. It's pretty state of the art, and basically we'll use it to the images I showed you are actually captured from this scope. So that's what you'll use to see what's on the card. And then, so how many of you have worked with this one before? Okay, about half. It's in 200 or okay, perfect. And how many of you used the digital capabilities of the scope? Okay. Perfect. So you learned something new. Very good. Very good. So this is a mixed domain oscilloscope, which basically means, maybe this is a bigger picture, that you can do both analog and digital signals. So the scope has either, depending on the version, either 2 or 4 analog signals that you can measure, but it also has a digital probe that we'll actually be using for the lab. And yeah, so we'll use the digital probe, and then this is the kind of the setup from the lab. So it's the same thing as here. So I've removed there's no analog cables, but basically you have a digital probe that has two of these breakout ends, and then you can use that to interface the scope to any sort of digital logic. So you have two 8-channel connectors, and then each connector has 8 cables corresponding to the 8 channels and two grounds. So together you can look at up to 16 digital signals in parallel with the 8 connectors. But this is a little bit bigger because you probably can't see this one. So each connector has again two ground wires, which are the wires on the end of the cable, on the sides of the cable, and you have the 8 color-coded wires for each of the channel. From experience, one of the channels is color-coded black, which is the same as the ground. So be careful whether you're connecting the black ground or the black channel. I don't know, they should have picked a different color, but in general, if you see black, you should associate with the ground. But anyway, they're labeled, and they're labeled, so that's most important. They're labeled 0 through 7 on both of the channels. So basically, so how do you work with the digital probe? So the idea is that the scope basically constantly samples the signal that's coming in on the digital probe, looking at the voltages, and basically you can configure how often it samples it. But when a signal comes in, it quantizes it into either 5 or 3.3, depending what the logic level is. So on the scope, you will get a kind of the square waves that we saw. So if you in 200, you probably you saw the actual analog signals that are coming in, whereas if you use the digital probe, the scope kind of automatically interprets the signals into a high or a low. And actually, if you want, this is also an optional part of the lab, you can hook up an analog probe to the digital pins that are coming out of the card reader, and you can see what happens. So most likely the digital output would be nice square wave, but the analog output might be something, I don't know, not so nice. So you can see what the scope. So the scope actually gets the analog voltages, and then the digital probe just converts it for you to a nice signal. And that's all great, but basically it's in real time. So how do you actually capture some data? So there's this notion of triggering, which I guess you probably used before as well. So the idea is that there is a special condition that's met by the incoming signals. The scope starts to save the data that it observed, and then depending on how much memory the scope has and how often it's sampling, that determines how much data you can save. So all right, so this is basically the scope setup before it's captured any data. So the lab manual will tell you how to connect the wires and configure the scope. And you can see again that there are 3 signals corresponding to, I believe, track 1, and then there are 3 signals corresponding to track 2. So that's exactly what you saw on the slides. And for example, the scope you can see here triggered. The scope is waiting for something interesting to happen. All right, so now we have all the information about the credit cards, kind of some information about the scope. Do you guys have any questions? Grand finale. Okay, almost there. So how do you actually read the credit card? So this is the final setup where you have the scope connected to the credit card reader via the digital probe. And then you also have the 5-volt supply plugged in. So this is, I don't know if you can see, but this is basically what we have here. You have the 5-volt supply, the digital cables, and it's been configured to capture the data. And again, there are 3 signals for each of the tracks. So you have track 1 and track 2 is connected, and don't forget about connecting the grounds. So there's a common reference for everybody, which is the ground. And then basically when you swipe the card, the lab manual will tell you to trigger the scope basically on the falling edge of this card present signal. So as you're swiping the card, it looks at signal number 5, which is the card present for track 1. So if the card you try happens to have something useful on track 1, when you're swiping it, at some point there will be a falling edge of the card present signal, and then the scope will start capturing what was written on the card, and you can already see that the card present goes low. There's the clock that goes up and down, and then there's some data that's going up and down. So you have captured what's on the card, and it's kind of hard to decode this. So there's a nice wave inspector function. You can press there's a little green magnifying glass that basically it shows you so this is the top, shows you all the data that the scope captured. The nice thing is that you can actually capture data before the trigger happens. So the T so this is when the scope actually triggered, but it's constantly capturing data. So so it captured something before and then something after. And that sometimes sometimes it might be useful to see what happened before the trigger. But in our case, we're just looking after the trigger. And then the little square brackets let you zoom in on this particular region. And when you zoom in, this is the picture I've been showing you. You can see exactly the clock and the data. And fortunately or unfortunately, there's much more clock and much more data that you might have to go through to actually decode everything that was on these tracks. Yeah, and so I think that's pretty much it. With this setup, you know, we have a really cool setup. We have lots of different credit cards, hotel key cards, whatever. Hopefully, you can, you know, kind of learn something, how to actually use them and find out what's stored on the card. So, do you guys have any last questions before I talk about the kind of the evaluation? Yeah.
So why is the card present signal needed? Because it looks like you could kind of just tell to start triggering or start looking this by looking at the clock signal when it went from all-time low to starting.
Yeah, good question. Yeah. So yeah, that's a good question. So so the card present, I guess basically it's I'm not 100% sure. You could probably get away without the clock. I mean, without the card present and start looking at the clock. My understanding would be that the card loaded or card present is when there's some actual useful data, and then the clock might start earlier or later. So that's one way. Perhaps another way to look at it is it's like an AND gate. So you only read out the data if this is 1. So that could be another some sort of a mechanism. Yeah, sometimes when you're designing things like this, it's good to put in some redundancy or some kind of overestimate the things that might be happening. So yeah, so I'm not 100% sure, but it basically could be either a mechanism to control kind of end the data output or just a redundant thing, so you don't rely on the clock. Any other questions? No? Okay. All right. So I guess the most important stuff. So how to do this project? So basically, there are two parts of the project. There's the project manual that will be posted within an hour or two. That basically tells you how to set up the scope. You know. Oh, actually, most important. You can't see it, but basically, if you look on the screen, you know, it will tell you how to set up everything, and then when you swipe the card, depending on, you know, how quickly you swipe, you can see that you can see the data changing, and the scope is actually reading stuff. So the manual will tell you how to set all of this up, and ask you to read one of my old credit cards. So if you basically set everything up and read read and decode and basically tell us what's stored on one of the credit cards and write it up as a project report, then you get up to 90% of the points for the lab. And then to get the full 100%, basically it's kind of open-ended, do something extra. So it's more about, I don't know, fun ideas and quality over the quantity. So if you, I don't know, so for example, one example is, you know, you can ask us, we can explain how to do the analog capture, and then you can compare, for example, the analog to digital signal to see what happens. Or, you know, you can analyze a hotel key card or a metro card versus a credit card. So if you do a bunch of credit cards, it's probably not as interesting or worthwhile if you maybe try one thing, but it's a different type of a card. So it's very open-ended, and you know, I hope everybody gets 100%. So just, you know, you can come up with different ideas and give it a try.
Do the metro card and hotel key card work inherently the same way, or? Yeah.
They're pretty much the same as the credit card. The idea is that we don't exactly know, for example, what exactly information is on the card. So you might have to do some reverse engineering to figure out, is it this encoding or is it that encoding, and try to figure out what's on the card. So for example, maybe you'll swipe the hotel card, and then you'll see there's a room number. You can see something that looks like a room number. So it's more of a, I don't know, more of a detective work. If you watch Sherlock, there you can kind of figure out what's the room number where somebody got mugged or something. So yeah, so it's they use the same standards. Up to 3 tracks, and then there's a limited number of encodings. But actually, I don't even know what's on most of these cards. So that's the fun part. It's kind of just tell us what's there. But you should have all the kind of the card reader and the scope should give you all the tools you need to understand it.
Will certain cards like change their output? For instance, like say you have like a gift card that has like a certain like set number of value on it, and then initially it'll decrease to down to 0. Will that ever change the output, or is that just some special way of counting?
Oh yeah. So the only way to change the output of this is to actually rewrite the information on the card. So that's a good question. I don't actually know how the gift cards work. I mean I guess the only way is you have to write on the card. So this is a card reader, so it has only one head for reading the field, but you could have things that has two heads. That the first one is reading, and then the second one is writing. But yeah, that's kind of I don't know. I think we have there's some gift cards there, so you can find out there's your 100% right there. So, but in general, it's static information. It's basically written on there, so you have to override it. Okay. All right. So yeah. So for some project logistics, we have 5 minutes left. So for project logistics, basically again, there's a 1 weekly lab session that you should sign up to and you should go to. Nominally, going to the lab session should be sufficient to complete the project, but especially for the later projects, you might have to go on your own time. So please go to lab as needed, not just during your assigned lab session. During the assigned lab session, one of us will be there to answer questions, but I hope that most of the stuff is in the manual, so you can get started early. Definitely come to lab session with questions. And then, so the project manual will be posted on the Friday preceding when the project starts. So I'll post it today, and technically the project starts next week. But you're welcome to. Well, actually, I guess there's no open lab hours yet. So starting next week. Okay, so you have to hold tight until Monday, and then you have two weeks to complete it. So basically, two Fridays from now at 5 p.m. Eastern, you can submit the report on Canvas. And I don't know, just start early, have fun. It's probably difficult. Don't try to break the stuff, but the card reader is pretty resilient. So you swipe different cards through it, and I think that's it. Oh, and most important, acknowledgements. So Kevin Ryan, as usual, for all the help with setting up, and especially he built the PCB last year, and Wen and Wenjie kind of help to debug this lab, and they'll help you in labs as well. So thank them for all the work. And I borrowed some pictures from the internet, so you can find the originals. And and I think that's it. So thanks a lot. I don't know, any final questions? If not, you can run home.